Hello, my name is Joe Barth. I'm here at the first MUGI virtual conference that I've ever done, and so if it's new for you, it's definitely new for me. I'm looking forward today to talking about renewable diesel and give you an overview of what that is and how that fits into our refinery product mix and how we plan a little bit more about diesel in this renewable environment. A little bit about my background. I worked for ExxonMobil for 33 plus years. The latter half of that career was mostly about refining, petrochemicals, planning, and optimization. I retired 18 years ago and joined Solomon Associates in Dallas, where I worked in planning and optimization consulting for another 14 years and then another 2 years, half-time, and now just retired. So I call myself a consultant emeritus. I still pick up a few jobs here and there where people need some help, and I still enjoy that, but mostly I'm doing volunteer work and other things. At any rate, so about our conference today, let's proceed. Before we start, there will be perhaps assistance needed. On-24 staff is monitoring this semi-live session and will be able to help if we have any technical difficulties. Time management is important. We don't have a lot of time. And as we go along, if you have questions, there is a Q&A chat box, and or please gather those questions and forward them to me for later analysis by email, and I can follow up on those. So here's the agenda for this talk. I will talk about our seminar goals first, and then we'll lead into what is diesel, a little bit of review of how the diesel engine was developed and the chemistry of diesel fuel, and that leads us to how we typically produce diesel today, and then we'll move into talking about renewable diesel, the current terminology that's used to describe renewables, and backing up to a bigger picture of what is the diesel market, and then how do renewables fit in. A quick look at the industry production plans. This will be a snapshot. It's a highly dynamic area that's changing and will need to be updated continuously. And then what are the economic drivers and other drivers for renewable diesel, and why is the industry embracing them? And then we'll wrap up with a brief summary. So, the goals for this presentation are to give you a high-level overview of renewable diesel, what it is and why we're concerned about it. We are going to be focusing on the known situation. I'm not going to get into forecasting wild cards of what might happen or not happen in the future, but just what we know at this time. We'll be primarily talking about the United States, although there are global interactions that are important. We will compress a lot of information into a short period of time, targeting for 45 minutes, and things are in a high state of flux, so anything that you see might be changing rapidly in the future. And then we'll be gathering any points of interest for future follow-up. Talking about the quality of the information we have here today, this information is in a rapidly changing area of renewable diesel, so expect that whatever you hear today is probably going to be changing. To my knowledge, all the information I have found here is in the public domain from various sources. Nothing is proprietary. It needs to be protected in that regard. The other thing you'll find is that the terms, when we talk about renewable diesel, are certainly not standardized at this time. And so, be cautious when you're comparing reports and data from different sources. I will also add that the dimensions and amounts of renewable diesel seems to generally be included in what we call biomass as an energy group when you're comparing data broadly from other energy sources such as nuclear, petroleum, coal, natural gas, solar, wind, etc. So biomass may include renewable diesel. Again, terms are not quite settled yet. And so be careful, because renewable diesel data can be sorted in many different ways. So as you're digging into this, be careful to sort your data appropriately. Let's begin by talking about what is diesel. How is diesel produced in the industry today, and what are some of its properties, and how does a diesel engine work? The diesel engine was developed by Dr. Rudolf Diesel, a German who studied engineering at the Technische Hochschule in München, and his goal was to improve the fuel efficiency and energy efficiency versus alternative spark compression engine or steam engines. He developed his compression ignition engine in the 1890s, and it was first patented in 1892. In 1895, he founded MAN, or Maschinenfabrik Augsburg and Nuremberg, which is a good company today. His engine was tested successfully with a wide range of fuels, and it was originally developed on peanut oil. He found that he got very good performance with carbon molecules that were in the C12 to C20 carbon number range. Here's a picture of the first diesel engine. It's at the Museum of Technology in Augsburg. And this first engine was one cylinder. It was about 3 meters high, and it was patented in 1893. Quite a big flywheel you see there. So, Rudolf Diesel's first most efficient fuel was peanut oil, and that's the start of the story of renewable diesel. He had one problem, though, or we all did, and that was there was not enough oil for fuel supply for his engine. We look back in the late 1800s, agriculture and marine culture were limiting oil sources. Cod oil was being exploited, farming was at a small scale, whales were being hunted to extinction, and forests were largely being cleared. However, parallel with that, there was a new development, petroleum. So with petroleum, it was discovered that there were these diesel boiling range materials that were in natural petroleum. Petroleum itself is a mixture of molecules from methane, 1 carbon number, up to larger than asphalt, over 100 carbon numbers. These molecules consist mostly of carbon and hydrogen. They're therefore called hydrocarbons, but they can contain other atoms such as sulfur, nitrogen, oxygen, and those are called heteroatoms. The absolute composition and properties of crude petroleum vary a lot, and it depends on the original geochemistry. The diesel anomaly carbon-12 to carbon-20 range is typically about 30% of crude oil's yield in composition. In that same range, we have jet fuel, which is typically 12 to 16 carbon numbers, and that can be separated from the diesel range, or it can be included in diesel. The refineries typically recover diesel from crude oil and can also convert larger molecules, heavier than 20 carbon number, into the 12 to 20 range through processes called conversion. Let's look at some of the key qualities for diesel fuel. Some of these include cetane, or its burning properties. The reference is normal cetane, which is a 16 carbon straight chain molecule, and it in a test engine has a reference performance of 100 cetane. The cetane is a measure of the tendency of the fuel to knock. In other words, that's the unoptimal ignition of the fuel. And the specification for finished blended product diesel is typically in the range of 40 to 50 cetane number blended. Lubricity is important because it's the viscosity required for the dispersion of the fuel and preventing wear of engine injector fuel. Sulfur is another important property. Sulfur causes corrosion in the engine, but we can mitigate that with a proper lube oil program. And also sulfur burns to form sulfur dioxide and sulfur trioxide emissions, which are environmental concerns. Very important in diesel are what we call the low temperature cold characteristics. Two of those are the pour point. In other words, for this diesel fuel, as we lower the temperature, at what point does it no longer flow? Yet another is the wax appearance point. And again, as we lower the temperature of the diesel, at what point do wax molecules or solids tend to form in the fuel, and that causes a problem with filter plugging for the fuel system. We want to make sure that the diesel is safe to handle, and the property there we mostly watch is the flash point, which is the temperature at which, with a spark, the diesel will ignite. In other words, you raise the temperature, and at some point it will ignite. That's what we call the flash point. And yet another and last is stability. It's very important for storage. We don't want the oil to degrade with storage, forming gums and other problems that will foul our engine storage system and combustion. Let's talk about how a diesel engine actually operates. It's called a compression ignition engine cycle. This chart was from my good friend Mark Hoffman over at Auburn University. If we look across here, we see 4 cross-sections of a diesel engine. Let's start with the one on the left. On the one on the left, we have a cross-section of a cylinder. We have the piston here that's coming down off the crankshaft. And as the piston's coming down, there's a valve that's open that lets air enter to the cylinder. And when the piston reaches the minimum, it starts up. If we go to the second photo, we see that as the piston is going up, what's happening to the air? It's being compressed. And as we know, as we compress a gas in a fixed volume, it becomes hotter. And so in that compression step, we are making the air mixture hotter and hotter. When we get to position number 3, we inject the diesel fuel. At that temperature and pressure, we have auto ignition, and that causes an explosion, which drives the piston down, and that's how we get to position number 4, and that's where the power comes from, the piston going down and creating energy into the crankshaft. And as the piston's coming back up, we open the valve to the right, and the exhaust mixture in the cylinder is expelled. So now that we understand a little better about where diesel comes from and a little bit about its properties, let's talk about renewable diesel, and we'll move on to talk about the diesel market. This is my rendition of where renewable diesel stand. I say that renewables are hydrocarbons that are alternatives that come from living plant and animal sources. They are not from petroleum. That's why we call them renewable. And currently, I'm going to put those into 3 renewable diesel prospects. One, you mostly hear about, is biodiesel. And this typically is fatty acid methyl ester, which is easy to produce. It's what I think of as the first generation of renewable diesel. And it's essentially most of everything you hear about today. It has limited production, and it has some quality and compatibility issues that we'll look at. Flame is also hygroscopic, which means that it absorbs water, and so it has to be carefully handled as far as logistics are concerned, because we don't want wet diesel. The next group of renewable diesels is hydrogenated vegetable oils. Now, this is what you're hearing more about as coming into the market, or HVO. It's the next generation, and it requires hydrogen processing, and the product therefore becomes compatible and is quite useful in petroleum diesel mixes and in diesel engines. The last tier is Fischer-Tropsch. Fischer-Tropsch has been around for a long time. It's well-established technology. But to be renewable, the feed has to be from a plant base. In other words, an example would be switchgrass or other plants. And so it's an excellent quality, but it's currently very expensive to produce. So why not just burn raw waste oils from as fats as diesel fuel? Well, my friends that are in the industry tell me to make emphatically sure that we express that this is no, no, no. These unsaturated fatty acids have lower oxidation stability. They react with oxygen in the air to produce oxides. They degrade in order to produce products that cause sludges and lacquers in the fuel system. These natural oils also have lower thermal stability, and so they gum up in the diesel engine, injectors, pistons, rings. They gunk up the engine grooves, cause sticky rings, and, well, it's just not good for the diesel engine, and the disastrous results can happen pretty quickly. So, no, no, no. So let's visit this first generation of renewable diesels, which I think of biodiesel today. You'll hear biodiesel and renewable diesels used interchangeably in sources. I like to separate them and use my terms of renewable diesel. But fatty acid methyl ester is one of those. The base is a fatty acid vegetable or animal oil. And by nature, this is rancid material. If you've ever had old oil hanging around the house, you know it turns sour bad. And then that acidity causes corrosion problems. Now, we can correct that by turning it into an ester, and that reduces this issue of corrosion. It's relatively simple and can be done in small batch processes. It needs a catalyst, which can either be a strong acid, such as sulfuric acid, or a strong base, like caustic. And molecularly, what we take is that fatty acid, and we react it with an alcohol, and we therefore get this fatty acid methyl ester, and we also get a byproduct of glycerin. My friends at Auburn in chemical engineering say that a good opportunity is to somehow recover this glycerin in this process economically. As it is very dilute, and there's a lot of other impurities in the glycerin phase. And so it's just gone to landfills right now. But glycerin is a valuable product. You and I use it, and that's a different subject. But if we could recover that glycerin economically, it would really boost the attractiveness of FAME. So let's talk some more about this renewable diesel FAME properties versus petroleum diesel. FAME has good cetane. It's about 56 versus 50, and that 40 to 50 is a typical spec today. It's a little bit more dense. That's not a big issue. The FAME energy content is a little bit lower, not drastically. The CO2 equivalent emissions is a little bit favorable versus petroleum. But FAME has an issue with what is called wax formation. It's not actually wax. These are solid particles of glycerides that do form in plug filters. Also, FAME oxidation stability is poor. And so FAME causes engine injector corrosion and spray blockage. It can affect elastomer seals and cause failures, and so it's really difficult for engines as we design them today to handle them. Engine manufacturers and therefore pipelines limit the FAME in a diesel blend to 5 to 7% of the product diesel. And we in the industry call that the blending wall. That blend wall limits the amount of FAME that can be blended into diesel. Additives have helped to some extent, but this blend wall had limitation on FAME blending will not meet some of the goals that are in place for replacing petroleum diesel with renewables. So as we just said, this blend wall for these so-called biodiesels limits the amount of renewable diesel that can be made with that convention. Let's put that in perspective by looking at total diesel demand around the world. Wherever I'm using public domain information, I will cite it on the slide. In this case, it's the BP Statistical Review of Energy from 2020, it's 2019 numbers. I think that's good enough. Numbers for the year 2021, 2022 are not available yet, and with COVID effects, I don't think they're as reliable. But take a look at this slide. If you look on the left-hand side where we talk about consumption, there's a couple columns, but the one I want you to focus on is total oil. And you see that on a total worldwide basis, the world demand for total oil is about 99 million barrels a day. I use 100 million barrels a day as a reference. In the U.S., that's about 19 million barrels a day for all purposes. And part of that is diesel and part of that is kerosene for jet fuel. If you look over here to the right-hand side of the chart, we have reported all biofuels by the BP convention. As I just said, biofuels, by my thinking, is a subset of renewables, and it's primarily FAME. And you can see the volumes produced worldwide and in the U.S., and you can see the percentage of total oil that's produced and as a percentage of diesel. Currently, all the biofuels that are being produced are being consumed as diesel, but some of the molecules could be separated as jet fuel. So you can see it's a small percentage of the total diesel demand. And to reach that 5% renewable diesel target that has been set, renewables would then have to double. And we're going to have a hard time doing that with conventional purposes. So what's in the press today are the next generation of renewable diesels, and these are hydrogenated vegetable oil. People call it biodiesel tomorrow. This HVO is the second generation. The base is still vegetable oil or animal fats, but it's hydrogenated to treat the acidity issue that comes with these natural oils. sometimes we can hydroisomerize to improve some of the low flow properties by using hydrogen. And we have established technologies that we use in refining and petrochemicals and food processing to do this. It does require hydrogen, and large scale fits well into existing refinery configurations that typically have hydrogen production. It is more costly than today's conventional FAME, or what we call biodiesel most of the time. There is a trend toward what's called gray diesel, a gray hydrogen today, and that is from steam methane reforming. It is the lowest cost source of produced hydrogen. And here we're talking about basically taking methane or some other hydrocarbon, reacting it with water to produce hydrogen and carbon dioxide. If electricity was cheap enough, you could use electrolysis of water to produce so-called green hydrogen. HVO has low lubricity, and so additives have to be used, but those have been developed. And energy companies are thus pursuing these HVO investments, and that's what you're reading about in the press. We'll look at a little bit later. So it does improve the diesel quality. It eliminates most of that blend constraint. It fits nicely into existing refinery schemes, and it can produce a jet fuel fraction that could be separated and sold as renewable jet, and it is scalable. All you need is enough vegetable oil and sources and get that logistically to the new production site. So let's talk about industry production plans. These have been in the press, and it's a pretty active area, so dynamic, the timeline and the scope of these projects are going to be changing, and so whatever we have here is a snapshot. But let's take a look. So let's look at where renewable investments have been announced. One reference is for U.S. renewable diesel production that it could reach 330,000 barrels a day by 2024. The source is by the U.S. Energy Information Agency, published in Hydrocarbon Processing last year. And put that in perspective, in 2019, as we saw, U.S. biodiesel production was about 96,000 barrels a day, so that's a considerable increase. We talk about other investments, large scale, that have been announced. Well, Neste has been the world leader in renewable diesel for some time. They are the leader in hydrotreated technologies for vegetable oil and animal oils. They have a proprietary technology that can be licensed, and that has been led by their investments at their Porvoo refinery in Finland. In two phases, Porvoo 1 and Porvoo 2, they have added biodiesel, renewable diesel production on an industrial scale, and the last expansion was in 2009. So they've been established for a while. They have announced big investments for Rotterdam, large scale, about $1 billion investment, and they've teamed up with Air Liquide to provide the hydrogen for that source, hydrotreated vegetable oils. And yet another big investment in Singapore, gathering vegetable oils from that region, another $1 billion investment, and it's also teamed up with Air Liquide. So in total, by the end of 2022, just this year, if everything stays on schedule, Neste could be producing 90,000 barrels a day of renewable diesel. Another major investment for renewable diesel announced is by ExxonMobil. Source was hydrocarbon processing about a year ago. ExxonMobil has contracted to produce renewable diesel with a partnership with Global Clean Energy in Bakersfield, California, for the California market. And Global Clean Energy has a process that's patented that grows a better yield of cover crop that produces the oil for vegetable oil. ExxonMobil has a proprietary hydrotreating process, EMBD, renewable diesel hydrotreating. And Exxon's been big in hydrotreating, hydroprocessing for a long time. And this is going to expand on bio-dewaxing, an extension of what they've done for lubricants and diesels for a long time. They have a 20,000 barrel a day hydrotreated vegetable oil project and planned for their big Strathcona refinery in Alberta for 2024. This particular project will include carbon dioxide capture from the steam methane reforming and re-injecting that into underground storage where it will be used to help recover conventional petroleum. Exxon, therefore, will be planning to provide about 40,000 barrels a day of renewable diesel by 2025. So let's look further. I think what you'll see is there's quite an array of approaches to making renewable diesel. One is Marathon. They are going to be using waste vegetable oil and use the term WVO. They're going to be converting it into FAME. They have a plant up in Dickinson, North Dakota that has already started up, and they are planning a 48,000 barrel a day Martinez, California operation that's to start up next year. Valero is also in the business. They call their product Diamond Green Diesel, and it's going to use used cooking oil, they call UCO, in order to create a hydroprocess material. They're using a UOP technology and plan to have a plant in their St. Charles, Louisiana refinery, as well as one in their Port Arthur refinery starting up next year. BP has announced a plan for their Cherry Point, Washington refinery. They're going to be using co-processing, which means they're going to be mixing waste oil with conventional diesel and processing it together that way. Startup is supposed to be this year, 7,000 barrels a day, a $45 million investment. Phillips 66, yet different approaches. At their Rodeo, California refinery, they're actually going to be converting their refinery to just produce renewable diesel. They are going to be starting up a hydrotreater early and then expanding that, and they're using topsoil technology for their hydrotreating process. Their goal is to convert that refinery into a 50,000 barrel a day renewable fuel operation by 2024, and at that point it will be the world's largest. And they also have an investment at their Humber, UK refinery, and there they've got a sled-mounted cooking oil renewable diesel operation that they're planning. It's 1,000 barrels a day, and it comes with a completely mounted operation that they'll tie into the refinery. And there are various others. But the scale of any of these remains small in the scheme of diesel requirements, and they're also relatively expensive. So let me have you think about the scale of this hydrogenated vegetable oil using waste oils. Just think about it for your family. How much vegetable oil do you consume per year? In our home, maybe we consume 1 liter per month. Typically that is canola oil, which is called rapeseed oil, particularly when we're making diesel. But we also consume some corn oil, soy oil, olive oil, coconut oil, sunflower oil, palm oil. So maybe in all, we consume maybe 3 gallons a year. And how much waste oil do we produce? Well, we actually consume most of it as food, so maybe 1 gallon a year. So we are not going to be generating a lot of waste oil. And then how much petroleum do you directly consume? I reckon I consume maybe 1 gallon a day, because I drive maybe 25 to 30 miles a day on average. So renewable diesel, waste oil, I'd say is just a small scale. So vegetable oil has limited potential for making significant volumes of diesel. However, the third tier of renewable diesel horizon is Fischer-Tropsch, and it basically gives us an unlimited potential renewable diesel. Fischer-Tropsch can potentially upgrade any carbon source, such as switchgrass, and therefore it becomes renewable. The technology in the literature is often called BTL, biomass to liquids. Fischer-Tropsch itself is an established technology. It was developed back in the 1920s by Fischer and Tropsch, and has been widely commercialized. Originally based on coal in Germany and South Africa. Since then, a lot of coal to liquid production, and also natural gas as a carbon source. And the major plants doing that are in South Africa as well as Qatar. And Qatar has 2 major plants that are converting natural gas to liquids. What we're talking about here to be renewable, though, we need a non-fossil fuel source. And so switchgrass and other sources are being researched. Energy companies are actively pursuing that in R&D. A lot of that is being done by universities that continue to do the research. It's still very expensive, but it does have the potential of being very scalable. It is capital intensive, but plants of various size can be built and fit into existing refinery configurations. So continue with renewable diesel. From a biochemistry point of view, there are big opportunities. So if we could have plants capture carbon dioxide to produce renewable diesel, that could be a win-win. And one of the greatest potentials is algae. Algae can grow very, very fast. And so can we convert algae mass into diesel? Can we use Fischer-Tropsch as the carbon source from algae? Or are there enzyme and other conversion processes? This is frontier R&D. And again, universities are actively looking at this. And again, it can be scalable because nature produces a lot of algae. And if we farm the algae, we have almost an unlimited source. And it doesn't compete with food. So we've discussed some of the activities that the industry is taking in order to make renewable diesel. So what are the drivers for this? What is making the industry do this? And it's largely a very green effort to make this happen. The primary drivers for renewable diesel are mandates. In Europe, the EU is controlled by what's called the Renewable Energy Directive, or RED. RED Phase 1 required that 7% of FAME be in diesel blends. Remember, that is the first phase of renewable diesel. The new RED 2 increases additional HFO, or hydrotreated vegetable oil, up to an additional 10% of blend. And by 2030, RED 2 requires 14% of all road and rail fuel must be renewable. Big drivers for the industry complying. The Canadian Federal Fuel Standard requires 2% renewable diesel, and the provinces which have more autonomy can mandate higher levels to meet these greenhouse gas reduction targets. In the U.S., renewable fuel standards are set by the federal government. Producers or importers have to either blend renewables or obtain blend credits. Complicated tracking of these blend credits is managed by what we call renewable identification numbers, or RINs. Very complex, and these are typed by renewable fuel based on feedstock, fuel type, energy inputs, greenhouse gas reduction, a very complicated accounting for renewable effects. And in California, the low carbon fuel standard provides subsidies and mandates for even further reductions. So these mandates are setting the stage, and what we know is that the market will respond. Let's look at the economics of renewable diesel. I put this slide together a few months ago, and I've been reluctant to update it because the markets have been quite unsettled here recently, so any snapshot now would be probably distorted. So if we look back at a more normal time, where would we find price information? Well, there are various price data sources. One of those is Platts and others that offer real-time price data, and that's very useful for commodity traders who are dealing with day-to-day, hour-to-hour trading. For us observers, it's not quite daily prices we need. Typical prices are good enough. So two sources to point you to are New York Harbor Diesel, that you can get an idea of Atlantic Basin landed diesel cost, and FAME, which is priced out of the Netherlands. So the current market, when I checked, was in response to these mandates and constraints that diesel in New York Harbor was trading at about $107.50. That's finished ultra-low sulfur diesel, similar to Euro 5. And FAME in Rotterdam was trading at about $335 per barrel. So why would a diesel blender want to buy Rotterdam FAME and put it into diesel with that kind of price differential? It's mandates. Mandates are driving the decisions. So since this is a MUGI Haverly LP modeling, conference, we have to talk about the impact on our LP modeling of renewable diesels. Modeling renewable diesels, if you're already not doing it, is quite easy. For what we need to do, we need to input the diesel component blend qualities, such as density, cetane, sulfur, whatever your model requires. And then we need to provide the landed cost of the renewable component, and that could be various components that you're considering blending into your diesel pools. We need to put composition blend constraints so that we can control the amount of diesel or blendable renewable diesel going into the blend. And then for us planners, we need to have prices that are consistent with the other raw materials and products for the case that we're running. It's pretty easy to do this. Then you will see that the renewable diesel will be selected or driven by constraints in order to meet the requirements. People ask, should we be modeling the cumulative renewable blend credits? I say no. I think that's well outside the LP model optimization. It could be a factor in setting the constraint targets in the LP, but keeping up with all those credits, which are typically reported cumulatively per year, is outside the LP model. Better tracked by other tools. Excel spreadsheets are typically used, but other tools can help you track those credits. A question I have for GRIMPS users are any refineries modeling blend credits within a refinery model? None to my knowledge, but I'd be interested in your comments. Let's wrap up the presentation. Overall comments: transportation fuel consumers like you and me are coming under increasing pressure to reduce fossil fuels consumption and carbon footprint because these are believed to contribute to climate change. Renewable energy, including renewable diesel production, is largely in a state of change. The third comment is the cost and economic concerns of implementing renewables are no issue for those committed to saving the planet from climate change. So be prepared for more change. And looking back, originally steam and horsepower had limitations in a growing economy. The gasoline internal combustion spark engine gave us great flexibility for small-scale engines. Rudolf Diesel invented a more efficient internal combustion engine, and internal combustion became the main motor of ground transportation and agriculture. Internal combustion vehicles revolutionized life in the early 1900s with commercialization, and that change was driven by lower cost and more flexibility. So the good news is, looking on to the future, renewables can increase today's systems, and this change will be driven by lower renewable cost and more flexibility. So be prepared for more change. It's coming. I'd like to thank a couple people who helped with this presentation. My friend Steve Benwell at Infinium in Houston was the expert that I know of when it comes to additives and the impact of renewables, and especially diesel. An old mate, Greg Marshall, is the expert I use when we talk about hydrotreating, hydroprocessing. Dr. Mark Hoffman over at Auburn is a mechanical engineering professor, and he's helped with understanding the diesel engine itself. And Dr. Mario Whedon, who's the chair of the chemical engineering department at Auburn, was helpful in comments about Fischer-Tropsch, which Auburn is doing research in. Thank you for all and anybody else who helped with this presentation. And so in conclusion, and for your future reference, if you want to look further in these fields, here are a couple of resources I thought were very good. Basics about renewable diesel has been published by Neste, and I find that a very good general use. On U.S. regulations and incentives, there's a good source there from Energy and Government. And then for market price information, if you want to look at some of these driving effects, here are a couple market price sources that you can use. They won't be real-time, they'll be recent current, but they can give you an idea of market conditions. Thank you very much for allowing me to make this presentation. I hope it's helpful. So as follow-up, if you have any other questions or input about this discussion of renewable diesels, I'd be glad to discuss those with you, either during this MUGI virtual seminar with follow-up, or you can contact me at any time at my email, which is joebarth as barth.opc@att.net, and I'll be glad to chat with you about other developments in this area and changes that are going to be coming forth here over the next couple of years.
All right, thank you, Joe, for that great presentation. We are now going to take a couple minutes to answer some of the questions that have come in through the chat box. So go ahead and take it away, Joe.
Okay, well, one of the chat box questions was from CEEW over in India, I think. And the question was, about 80% of the petrol demand in India is for two-wheelers. And if they were electrified, would refineries move to higher production of diesel and jet fuel, and how will this play out? Well, what we're therefore talking about is a reduction in transportation fuel and the mix, and so we don't really know of a way to replace jet engine fuel yet. And so that would continue to require petroleum production for jet fuel, diesel probably for heavy rail, which India depends a lot on, and then, of course, marine fuel. So it would shift the slate. We would look for processes that favored diesel. I just saw a highlight today in the American Institute of Chemical Engineers that refiners are doing everything they can to make every drop of diesel in order to increase shipments to Europe because of the current imbalance, continued imbalance, which has come only more so recently. And so, yeah, that's just going to be a change in the product mix. And if the total volume goes down, then the requirement for even having refineries is going to go down. And those that survive are going to be changing their mix. Petrochemicals are another way of producing products from petroleum, and of course that's a separate growth rate, and refiners are integrated usually with that for feedstock and so forth. But yep, as we electrify vehicles, we're going to replace that energy source from petroleum or to electricity, and however we generate the electricity. Another comment was from Randy Segato up in Canada. And yes, the Canadians, as I mentioned in the slide about Canadian requirements, that they have been advanced versus at least the U.S. as far as planning renewable diesel and environmental impacts. And so my comment was trying to get the exact small increment of trade and so forth, I think is impractical in a model. But I think setting up the guidelines for what our requirements are is very practical, and so I'm inferring that that's what Suncor is doing, something like that. And then a question from Hellenic, and that question came in early in the presentation, and I sent a text message back to say, look at those slides of current industry plans between Neste and others, and you can see that I didn't find any two major companies that are taking congruently the same approach. They're all using different approaches, different sources of oils for hydrogenated vegetable oil. There's various technologies that Topso and others are offering to hydrotreat this material, and so it's very diverse right now. And so what I might suggest in the case of Hellenic is to maybe look at those companies that are doing something more akin to what you are thinking your scheme would be, and study them in more detail and get an idea of what they might be doing. I don't see any other questions.
It looks. Did you answer Randy Segato? Any experience you've come across yet on biocrudes?
Okay, I'm reading Randy's question right there. Okay, so these are, all I'm taking Randy's comment as these biocrudes, but really synthetic crudes be they renewable types or whatever, and whether we feed those into the front of the refinery or cat cracker or whatever. I would say that what we need is the characterization, and we have fed alternative streams to petroleum into cat crackers, for example, before, such as streams that come out of steam cracking, other sources. And so what we need to do is just characterize those as a feedstock and build those into the model. So that characterization depends on what your cat cracking model requires. For rough screening, I think you could put in the best characterization you have and see how it fits. I think to actually plan on a commitment, then, of course, you need to do some detailed work on a better characterization of those feedstocks and the variability of it and get more precise. But the beauty of the LP is if you've got some rough numbers that describe the properties you need for your cat cracker, put them in the model, see what the valuation would be and how it fits in, and you get a rough idea right there. But again, depending on the sources and so forth, you need more detail, Randy. And then
Great.
Richard Tan was saying that CHS is modeling RIN in their group's model. Good.
Great. Thank you, Joe. I think that concludes all of our questions for this presentation. So thank you, Joe, for all of your effort to put together some great content for us this morning. Our next presentation is going to start at, let's see, one second, I believe in 10 minutes, and that will be Vince DeVita speaking about what's happening in the LP world. So his presentation is going to talk a little bit about evaluating CI, integrating renewable operations into an existing refinery, co-processing opportunities in HDT, and network modeling for hydrogen and ammonia systems. So I'm going to go ahead and end this webcast for this morning, and we will see you all in about 10 minutes in Vince DeVita's presentation. All right. Thank you, Joe.
Thank you.